So we have a cylindrical drill with a radius of 3 to bore a hole through a sphere of radius 5. Find the volume of the ring-shaped solid that remains. Okay, so we notice we're trying to find, what are we trying to find here? Volume, right? Okay, so we're trying to find volume. So what can get us volume? That's the first thing we say. Double integral, right? So if we're doing a double integral and we're expecting polar coordinates because we're in the polar double integrals homework, we're going to have some function, right? Times r d theta over some region. So the question is, let's understand the problem, right? Let's draw a picture, let's understand the problem, and see how we might use a double integral, what we understand about double integrals, to help us solve it, right? So, sphere of radius 5. Okay, that's the best sphere I've drawn all day. Okay, and so with radius 3, we're going to drill with radius 3 right through it. So we're gonna drill down here with radius 3 like this. Oh, radius 3. So that would be this would be 6 then, right? If the radius of the drill, if I'm going to drill down like through this, then that would be the diameter. That'd be 6. And what will we see? So when we drill through that thing, we're going to zoom like this. Does that feel like what the problem's talking about? Okay, and so now they want the volume of what remains, right? So it's like a napkin holder. This is like a nice napkin holder. Cloth napkin. So how are we going to do this? So obviously we've got cylinder, we've got this sphere. We want to model that, right? We want to model that in R3. So how should we model this in R3? It's the easiest way to model this situation with the sphere and the cylinder cut through it in R3.
Do the sphere in polar and then do the cylinder in Cartesian and subtract the two?
Okay, yeah, okay, so you're a little bit ahead of my question, but yes, right. So where do I want to put this sphere? Do I want to make it floating out in the first octant? What's that? Yeah, make the easiest you possibly can. Put the center at the origin, right? So we're going to put the center at the origin. Something like that, right? And so then what is the equation of our sphere? If the center is there and has radius 5? No, the equation. If I said what's the volume, then I misspoke. It's going to be this, right? So that's the equation of our sphere. And so how are we going to then relate it to this? So now we need to get this volume here. We need to relate it to a double integral. We've got this equation of the sphere. So for instance, like what is F? Is that going to have to do with the sphere or the cylinder? The sphere, right? It's going to be this surface right here. And so that F is what? F is like Z is a function of X and Y normally, right? So what's that going to be? What's that? Well, we're not there yet, right? So we just need a function first, right? Yeah. Right, so we're going to solve for z. When we solve for z in terms of x and y, then we have a multivariable function, which is this surface, right? Awesome, right? So yes, exactly. So taking the square root, we'd have a plus or a minus. The plus being the positive z's or the top half of the sphere, the minus being the negative z's or the bottom half of the sphere. But he's saying, let's just do the top half and multiply by 2. So we'll do 2 times a function, okay? And so then our z is our function is this is going to be our function. Okay, and then what is d? So now d is an xy plane or horizontal plane phenomenon, and it's what we're integrating this surface over, right? It's the region that we're going to integrate over. So what do we want to integrate over to get the right volume? So we want to consider the sphere over what in the xy plane. So what do you mean the ring that the drill makes?
So when you bore the hole through the sphere, if you just the projection of the top of the sphere, so the ring.
Okay, so our sphere projects like this with what radius? 5. And then? What's that? And that, yep. Man, I should make it green here. That's my green cylinder there, so I'll make it green. Those are not the best circles I've drawn all day. Oh, not too bad. No, those are pretty good. All right, so then what? So what is our region D, right? So there's these double integrals really have 2 main parts. Is the surface that we're integrating with a multivariable function, and then over what region? So what is our region that's going to get us the volume that we want? So you were, Alex, what were you saying?
Well, in Cartesian, it'd be negative.
I'm not asking for equations right now. I'm saying what is D here? What is D?
It'd be the area between the green circle and the black.
Right, it's the region between, right? So if we were to integrate that surface over that region, we would get half of the volume that we want, right? And so this is like this is going to give us our limits, right? D will give us our limits of integration. The function f, the sphere, gives us our multivariable function. Don't forget the r. I'm just gonna let you do the rest now. You might have different numbers, so make sure that you have the radius of your drill and your sphere right. Questions on this one? Is this good enough for you to go and finish this one up? Yeah, so it's just a matter of taking what we learned about polar double integrals and then understanding the situation, modeling the situation in R3, and then asking, how would a double integral solve this question for me, right? And what are the elements of a double integral? We need the region that we're integrating over, and we need the surface, the function for the surface that we're integrating. So I think we're good on this one. Any questions on this one? Okay, next one. Similar situation. So we want a solid, it says consider the solid-shaped ice cream cone that's bounded by the functions. So what is this? Z equals square root of x squared plus y squared? What is that? Z equals square root of x squared plus y squared. Single cone, right? If you squared it, you'd get z squared equals x squared plus y squared, which is our standard double cone. So this is just the top half because it's the positive z-values. Okay, so we have a cone, that's z equals square root x squared y. And then z equals square root of 18 minus x squared minus y squared. What is that? That's the top half of a sphere, right? If we square both sides, move the x squareds and y squareds over, then we have a sphere of radius, what? Root 18. Okay. So they're saying it's going to be bounded by the functions z equals square root of x squared plus y squared. So is that above or below? Above the first one and below the second gives what they're calling an ice cream cone. So we'll have, they'll intersect like this. Something like that. I like more ice cream in my ice cream cones. But take what we can get, right? All right, and then so in the instructions, then they're being very polite here. They're saying, please enter the integrand in the first answer box, typing theta for theta, okay? So we want to set up a double integral that's going to get this volume for us. So our double integrals, what? They find the volume between a surface and the xy plane, right? So we need to think about how can we apply a double integral idea to get this volume, which is not between, it's actually between two surfaces, not between the surface and the xy plane. So now we've seen a similar situation in previous calc courses. We want, for instance, the area between two curves. This is similar. This is the volume between two surfaces. How are we going to use double integral to do this? Yeah, Daniel.
Subtract the bottom equation from the top one.
Yeah, so what if we were to do the double integral of the cone surface? What would it give? Would it give the volume up in here? If I just did the double integral of the surface of the cone, what would it give?
It gives you the volume
Underneath, right? Underneath. So if I do the cone, I'm gonna get this, right? I'm gonna get this stuff in here, which is not what I want. Okay? If I do the sphere, what will I get if I do the sphere? Everything from the sphere, what? Down, down. Okay, so if I do the sphere, I'll get a volume that's like this. Okay. And if I, no, yes. And if I do the cone, I'll get a volume like this. I get this thing here, right? And if I do the sphere, I get this thing here. So then
So would it be the sphere minus that cone?
the volume below the sphere minus the volume below the cone. Do you see that? Do you see how that works out? That if I take that whole cylinder with the cap and I subtract out the volume due to the cone, then what's left will be the ice cream cone that I want. So we could do two double integrals, but they want one double integral. So how are we going to do that in one double integral? So like double integral of sphere, right? Minus double integral of cone, but now they want one double integral. So it'll just be that you just have this sphere minus cone, right? It's all analogous to single integrals. All this stuff we did with single integrals, where if you subtracting, and they have the same limits, right? So do we have the same d that we're integrating over for both of these? That would have to be the case. Yeah, this is going to be that disk, right? That we're integrating both of those over the same disk. Therefore, we can combine them into one single integral and subtract the integrands in one single integral. Okay, got a roadmap for this one? Then this is better. All right. Any questions? So maybe maybe I'll make this one due at midnight tonight. I'll push it back to midnight, if that's helpful. Yeah, sometimes. All right, so let's push on. Here we go. Now we get to the fun stuff. Ooh, but I don't know which slide it is. Well, I've got 3 different slides. Let's see, which is the right one? I think this is the right one. We'll try this one. Triple integrals. Oh no, this is the one we've been waiting for. This is great stuff. Not as excited as me. And I've been teaching this every semester. It only gets better. Here we go. So triple integral. So the triple integral, so the way we're going to think about triple, just like we thought about double integrals from the inside out, okay? Same with a triple integral. We're going to think from the inside out. So the first thing we're going to think about is the inside integral. And so notice now our function, what? It's a function of 3 variables. So 3 variables. So where does this function live? Does it live in R3? It lives in R4, right? So it's what they call a hypersurface. It's something that is hard to imagine, but lives in R4. So therefore, when we talk about what we're integrating over, which is now no longer a region, but what we integrate over is what? We're going to step it up 1 dimension. So what we integrate over is a solid. We're going to call it solid E. And so the thing that we integrate over lives where? It lives in R3, right? So if we're in our double integrals, the surface that we're integrating lives in R3, and we're integrating that over a region in R2. So now we have some hypersurface in R4 that we integrate over a solid in R3. So everything steps up 1 dimension. Make sense? So when we're working out the limits of integration, we can still draw it because it's in R3. Just like we were able to draw the regions in R2 for double integrals. Okay, so therefore, we're going to start by, so remember we said our cheers were like bottom to top, left to right. So now the cheer is going to start as surface to surface, okay? Surface to surface. Surface to surface, and then once we get surface to surface, and then the outside is we're going to think of as just a double integral, like all the ones we've been doing before. So we already know how to do those. So double integral of what? So it's the double integral for the region as the solid is projected into one of the coordinate planes. So we're going to take that solid, that E solid, and we're going to project it, say, into the XY plane. Like, take the shadow of it, or if you just smashed it straight down, what would you get? You get a region in XY plane. So then this is what we know already. Once you've got that region, then you're going to do that. This is going to be a double integral. So you don't have to think of it as doing 3 things, but 2 things, right? Surface to surface, and then a double integral of the projection of E into the whatever coordinate plane we're looking at. So does that overall make sense? So it's not so bad because we've done all these double integrals, and so a big part of a triple integral is just doing more double integrals. Okay? Okay, so there's type A, and that's where our solid. So the solid is the greenish thing. that's where we're going to project that solid down into the xy plane, and that's going to give us our D. So this is E up here. This thing here is our solid E. And then when the surface to surface then is going to be, so our dV then is going to be, if it's this type A, then we're going to do dz first. dc, which means when we do surface to surface, it's going to be bottom surface, z is a function of x and y, to top surface, z is another function of x and y. So the cheer for type A triple integral is going to be bottom to top, bottom surface to top surface, and then the outside double integral is going to be what you get when you project E into the xy plane. That thing D. Does this make sense?
Is that supposed to be dz prime or just?
No, that's just something in my PowerPoint.
Okay.
Thanks for asking. That's what it's supposed to be. It's a very complicated PowerPoint with things covering up other things, so it didn't get quite covered up. All right, so that's type A. So then, like I said, the outside double integral is the region projected into xy plane. So this is type A. So when you do the double integral, you've got kind of three choices. You can have type 1 or type 2 or polar. So that's type A. Type B. Type B is where we're going to take that solid, and our surface to surface is going to be based on the picture here. What's our cheer going to be for the surface to surface? So type B is what's the first variable? So instead of dz, our first variable is going to be x, right? X will be first. And then so if it's x, then it'll be what to what? Back, right? Back to front. Back to front. If we're doing x first, right? So we're in the x direction. Back surface as a function of x is a function of y and z to front surface x is a function of y and z. And then our outside double integral will be in what plane? This isn't the right slide. Didn't finish it. I'm going to try the third one. Let's try this one. Surface to surface. So double integral, dA, bottom to top. Back to front. Here we go. That's the right one. So our type B, we're going to go inside integral back to front. That's our x variable. Then we're going to project into the YZ plane, the plane of the screen. And then we're going to do a double integral for that region D there in the YZ plane. Make sense? Finally, type C. So what variable do we integrate with respect to first? He wants y, agree? And then, what's the cheer? For the inside integral, from what to what surface? Left to right. Left surface to right surface. Those are functions of x and z, because we're integrating with respect to y. And then our projection into the xz plane. And then we're going to do a double integral in the xz plane of however that solid projects, or think of it as the shadow of it in the xz plane. Or if you just flattened it on the xz plane, what would you get? Okay, so we we got lots and lots of ways then. For each type A, type B, and type C, there's all the different ways we can do the double integral of the projected region. So there's all these different combinations, right? If you're just sticking with x and y and z, then there's actually 6 orders of integration. 6 orders of integration. dz first, and then dx, dy, and dy, dx. And then dx first, and then dy and dz, or dz, dy. And then dy first, and then dx, dz, or dz, dx. Okay, any questions on the overview here of what triple integrals are like? And so again, this is just, now these pictures are just thinking about what? How we set up the limits of integration, right? This solid E that we're integrating over. The actual function lives in R4. So we're integrating some function f over one of these, a solid in R3. Okay. So let's do an example. Let me find it. Wait a sec. What's that? Oh, wait. There should be a video. Hold on. So I made this for next semester to demonstrate torque.
Hey, bud, what are you gonna do? You gonna open the door? Show me. Push there, and open that door. Push, bud. Can you get that door open? No. Okay, we're gonna do. Show me, bud. Oh, so easy. Yeah, bud. Super Spidey strength. Say bye.
Bye, you did it on photo again.
The first time said, did you do it on photo again? Because the first time I just took a photo. Okay, so anyway, so next semester I'm going to show that to students when we're talking about torque. Show that it's not just the force, but also the lever arm, right? That is really important in the amount of torque. Okay, get back to work. Okay. Here we go. Let's see here. We need this. Okay. So I've got a tetrahedron here. Let's give it a spin. All right, so this is the tetrahedron, and this is going to be our solid E that we're going to integrate over. Okay, we're going to integrate over, and we don't care what the function is. It's plenty of work just to work on the limits of integration. So some function of x, y, and z that we're going to integrate over this, and we're going to work on setting this up in the different orders of integration. Okay. So first of all, we need some. What points are we at here? Here are the points. So we got 2, 0, 1. Write these down. So the corners of the tetrahedron are 2, 0, 1, 0, 3, 0, 0, 0, 0, and 0, 0, 4. So 2, 0, 1. The last one was 0, 0, 4. That's right. So what did I say? 2, 0, 1? And the first thing we need to do is figure out what all these surfaces are. Okay, 2 of them are quite easy, hopefully. And then one of them is not so bad, and then one of them takes some work. So we need to get these surfaces, because those surfaces are going to be the functions that we're going to have, like back to front, left to right, bottom to top, that kind of thing. We're going to need those surfaces in terms of x, y, or x, y, and z to write these limits of integration. So let me just pause it here. So what's a good view? That's a pretty decent view right there. Okay, so how about this back surface over here? Can we mathematize that? Can we model that back surface in terms of x, y, and z? This back triangle right here is all points on that plane have what characteristic? X equals 0. Isn't that the plane x equals 0? It's just restricted into a triangle, but this is just the plane x equals 0, is it not? Okay, hopefully most of you are thinking that. Okay, and then let's just do the other easy one here on the side there. So this one here, what is that? This right here. Y equals 0, right? That's just the plane y equals 0. It's the xz plane, right? It's the xz plane. So we got x equals 0, we got y equals 0. Okay? And then, so what? This was the point, what, 2, 0, 1? And then 0, 0, 0. So that can help us know what this plane is right here. So this plane, down underneath, it goes through the y-axis, right? Or the y-axis is contained in that plane. So we need to find that one. Find the plane where that contains the y-axis that also contains the point 2, 0, 1. And then the one that takes the most work is this front plane here, this plane that cuts through all three coordinate planes. So I'm going to take attendance, and I want you to come up with those equations of those two planes. This one underneath that contains the y-axis and the point 2, 0, 1, and then the plane that contains, or this plane here, that's the one that's it's cutting through all three coordinate planes. Work together? So this is review, right? So this is, but it's review from a while ago. So find the equation of those planes. Find the equation of those planes. Okay, so just a roadmap. So for time's sake, I think I heard a lot of you saying the right thing. So for this plane here, you're going to have to make parallel vectors, right? So you can make vectors between the points given. So those are two parallel vectors, but it doesn't matter. It could be the other way. Any two vectors that you make from those 3 points. And then what? What do we do from there? Cross product. And that'll give some vector, right? That'll be our A, B, C for the plane. And that vector will be what? Orthogonal to the plane. And then we need a point. We take any point that we want, any of these 3 points, and we use our equation of the plane, right? So our orthogonal vector ABC, and then any point x naught, y naught, z naught. You can pick any one of those that you want. And then if we want it, okay. So any questions about finding the equation of the plane? Are we good? Remember how to do that? Or do you remember now? Okay, so then when I do that, I get, where are they? If you're able to find it, I don't know if you made it this far. Z equals negative 3 halves x minus 4/3 y plus 4. You want to make it that far? You're heading there. But anyway, so this is the same plane written in the 3 forms. Z is a function of x and y, right? Y is a function of x and z. X is a function of y and z. It's the same plane, just rewritten as the various 3 different ways you could write it as a multivariable function. Okay, we're going to need that. Okay, so here we go. Let's start with something simple here, and we'll start with type A. And then, so then the double integral, we'll do type A1. All right, so type A1 would be, and again, these labels are just kind of our labels for communicating in class. There's nothing special about or intrinsic about these, what we're going to do that makes it A and 1. It's just the way that we set the label so we have something, a way to communicate, right? So what does it mean? Type A triple integral means what first? What's our first variable? Z, right? So first of all, whatever our function is, it could be any function of x, y, and z. And so then we want z first. And so then for z first, it's what to what? Just in general, when we do a type A, we're going from what surface to what surface? A couple of people are saying bottom to top. Agree with that? Yeah, because it's the z variable, right? So it's like the lowest to the highest. We go from bottom to top. So what was our bottom plane? Did anyone get that? Z equals? It's really just a function of x, right? Z values are just a function of x. What function of x was it? 1/2 x? Very good. Z is it negative? I think it's positive. Positive, because if we look in this, we look in the xz plane, we're just talking about this plane right here, which is x to the right, z up, that's 1/2 x. Okay, so z is 1/2 x. And I'm going to call these, so I don't have to write all this stuff out, I'm going to call these z1, y1, and x1. And those are all representations of this top slanted plane. Okay, so bottom to top means the bottom is z equals, that's our 1/2 x. And what's our top? z1, right? The top is this, written as a function of x and y. So rather than write this out, I'm just going to write z1, and then we know that it means this is z1 right here. Okay, and then the outside double integral is what? It's going to be for the surface that you get when you project that solid into where? XY plane, right? XY plane. So we can look at that. I can turn. And we can look at that. So if I look straight down on the XY plane, there's the projection of that solid into the XY plane. It's this triangle. So when you're doing the problems, you won't have the luxury of this 3D animation that you can just turn. You'd have to come up with that yourself. So can you see, just from a sketch, like some sketch like this, say, a little bit more, that projection is, so this, you can just, one thing that helps is project down key points. So project this point, that point will project down to there. This is already in the XY plane, so is this. So do you see that then gives that projection right there? So that's our D for the type, that's our D for the type A triple integral. Okay, so this point so then in the XY plane, so we'll sketch it. Leave it, it's like this. This point is the 2. Oh wait, this is 2, 2, 0, 1, so this is 2, 0, and this is 0, 3. Okay, so now given those 2 points, we have the outside double integral. If we do type 1, what was our cheer for that? Type 1 is which variable next? dy, then and dx, right? So now we're doing this, just now we're doing a double integral, right? Y goes from 0 to, we have to write this. We have to write this function. This is y equals, is that negative 3 halves x plus 3? Is that right? Plug in 2, you get 0. Plug in 0, you get 3. Yeah. So we're going to go from 0 to, should give myself more room. Negative 3 halves x plus 3. And then? Right, so then we're going to sum all those up with respect to x. So the first one is at 0, and the last one's at 2. So those are our limits. 1/2 x to that expression up there for z1, and then 0 to negative 3 half x plus 3, and then 0 to 2. All right, let's talk about type C2. So, perfect, awesome exercise to do all 6, right? Write down all 6. Great practice. But we'll go right to type 2 here. So type C2, what's the first variable of integration? Y first, right? Type C is y first, so it's going to be from what to what? From left to right. What's the left surface? Y equals 0. That's the left surface. Y equals 0. The right surface is? So from left to right, what's the right side of this? It's y1, right? It's now the right side is also this plane, right? So this right here, y equals 0, is the left side, and then the left side, and then the right side is going to be that plane. It's going to be y1, and we have to write it in terms of xz. That's why I did that. So it's going to be 0 equals, or it's from 0 to y1, and you would write this out, right? You would write this out as your limit of integration. Okay, and then if we're going to type 2, we're going to do what? From type 2 means what to what and what to what. So this is x, and this is z. I'm looking at the projection of that solid into the xz plane. And I'm going to say from what to what and what to what. Isn't type 2 left to right and then bottom to top? So left to right is which variable? dx. And then, but now the bottom to top is dz. So when we go from left to right, x goes from 0 to, what does it go to? This is split up, right? This is just like in your double integrals. So down here, when z is between 0 and 1, we're going to have one particular right side. And then when z is between 1 and 4, is it 1? Is it 1? And then 1 and 4? So when z is between 0 and 1, here's the z to 0 to 1, we're going to have be from 0 to 1/2 x. Is that right? That's this plane, this line 1/2 x. And then when z is from 1 to 4, it's going to be from 0 to, what's this point? This is 2, 1, and this is 0, 4. So we need the equation of that line, which looks like negative 3 halves plus 4. Negative, or z, sorry, z equals negative 3 halves x plus 4. So when z is from 1 to 4, this is just double integral now. So when z is from 1 to 4, x goes from 0 to negative 3 halves x plus 4. Did I do the math right? And it's the same left to right. It's the same left to right, 0 to y1. So this one has to be split up into two triple integrals because of the right-hand boundary of the projected region, D. Because that right boundary of the projected region is split, we're going to have the same surface to surface, we're going to have different outside double integral. Okay, get ready. It's getting fun now.